Hey everybody, welcome to Math with ACE. We are focusing on statistics today. We are going to be calculating a confidence interval for two proportions. And we're going to be doing this using a four-step approach where we state what it is we want to do. We plan by checking conditions. We do calculations using technology, and then we draw a conclusion. So this says a manufacturer is comparing two types of bicycle helmets to determine whether there is a difference in the proportion that fail an impact safety test. And we are going to estimate the difference in the true population performance of helmets that fail at 98% confidence. And the groups that we're dealing with is a random sample of 120 Unit A helmets where 18 failed, and a random sample of 110 helmet B units where 10 failed. So we're going to start out with our confidence interval statement of what we're doing. So we want to create a 98% confidence interval for, well, what are we talking about? We're talking about proportions here. So for PA minus PB, since they're giving us helmets A and B, the true population proportion difference in helmet failures from helmets A and B. Now, before we can actually run the numbers, what we need to do is make sure that our conditions are met in order to be able to use generalize to the population and use normal calculations to actually create these values for us. So we need to check our conditions. This is where we state. And we need to check random. And random is for both of these. So random sample of helmet A, random sample of helmet B. So both helmets A and B were stated to be randomly sampled. Independent, both sample sizes need to meet this condition as well. So for helmets A, there are 120. So 120 times 10 is 1,200. Helmet B, 110 times 10 is 1,100. This is a manufacturing company of helmets. I think it's safe to assume that there's going to be at least 1,200 helmets A and 1,100 helmet Bs. Now, the large counts / normal condition, however you are used to referring to it, is talking about successes and failures at least being 10 for both of these in order for us to be able to use that normal distribution. What that looks like is sample size A and the proportion from the sample A needs to be at least 10, and sample size A and the complement of those sample proportions needs to also be at least 10. This is referring to successes and failures. If you take the sample size times the sample, the proportion in the sample that are a success, that's going to give you your success value. Same thing with your failures. It's also true for sample size B times the proportion in B, and sample size B times the complement of that proportion. They all need to be at least 10. we're actually given successes. And this is terrible to say because successes are our failures of the test. So they're failing the safety test, but that is what we are worried about. So that is the success we are considering. We know that NA is 120, and the proportion from A is 18 out of those 120. Sample B is 110, and the proportion out of sample B is 10 out of 110, and these are the ones that fail. So now what we need to do is calculate successes and failures. So NA times P hat A is 120 times that 18 out of 120, which is 18. NB times P hat B is equal to 110 times 10 over 110, or 10, which is at least 10. That's true. 10 is at least 10 because 10 is equal to 10. So there were 18 that failed for helmet A, 10 that failed for helmet B. How many did not fail? It's the remainder. If you have 120 total, that means 120 minus 18 is 102. And for sample size B, 110, 1 minus 10 out of 110, that leaves 100. So there were 18 that failed in group A, 102 that didn't, 10 that failed in group B, and 100 that didn't. And our conditions are met, so we are safe to proceed with calculations. And what we're going to do is we're going to use Stapplet to perform those calculations for us. And because this is categorical, it's a yes, no, they either failed or they didn't. We're going to say one categorical variable, it's helmet failure, but we have multiple groups. We have group A and group B. So what that's going to look like is, make this a little bit bigger. We're going to say this is helmets. Group A is helmet A. Group B is helmet B. And we need to call this success, which is helmet fails. Feels kind of weird. There were 18 in helmet A that failed and 10 in helmet B. And this is failure, which is helmet didn't fail. Seems kind of weird. 102 and 100. And now we're going to begin the analysis. And we need to scroll down so that we can perform inference, creating the interval. And the interval is 98%, where we are talking about helmet failing. That gives us the interval of -4% to 15.8%. And this is estimating the difference as to whether helmet A and B do have a difference in failure or not. And when 0 is in the interval, we don't really have convincing evidence that there's a difference. That's hypothesis testing, but you can also relate that to your confidence interval. This is the same thing as -0.04 and 15.8, depending on how you want to write it. Now we're going to make our conclusion. We are, how confident? 98% confident that the interval, what interval? The one we just did. And what does it do? It captures, what does it capture? The actual proportion, PA minus PB, the true population proportion difference in helmet failures of helmet A and B. Now, I used lowercase a and b as I went further down, and I was using uppercase A. You really should be consistent. I should have stayed with capitalized or done lowercase to begin with, but A and B variables typically have different meanings when you're talking about lowercase versus uppercase. Hopefully this was helpful in working through the process. Thanks for watching.